I'm going to be introducing our first speaker, Jennifer Wong. Jennifer is a Master's of Science candidate in computer science at the University of Victoria. Her research interest includes fault tolerance in mobile collaborative systems and computer science education. She's been a member of Sparks, solving problems with algorithms, robotics, and computers, outreach research team, and is the volunteer coordinator of the Computer Science Volunteer Program. And she's here to tell us about communicating like Nemo.
All right, so hi everyone. My name is Jennifer Wong, and I am a grad student from the University of Victoria. Now, even though we have been trying to have a little bit of fun with our title, we do believe that there are serious research challenges in scalability in the family of devices that can possibly make a splash. Now, some of the issues that I'll be touching upon today will be with the scaling, involve problems with scale in the context of UI and communication between mobile underwater nodes. So today I've actually brought along a few questions with me, and I would like to ask for your help to make this more interactive and to answer all these questions together. Now, we've called our project the Nemo 2020 to tap onto the idea of having a perfect vision for the future. So even though underwater acoustic network are gaining momentum in the research area, we don't necessarily have cloud computing underwater yet. So I do need you to suspend your disbelief and just join me in this exploratory journey for the next half hour. So before we actually swim anywhere else, we'll look at a few of the current dive computers that are out there. Now, here we see three of the most common dive computers that are out there for recreational scuba divers. And so there's the wristwatch, there's the console, which comes with the standard scuba gear, and there's the face mask, which have the little LCD screen on the side for you to look at. And they're more or less showing the same kind of information using a text-based method. And they're solely designed for a single-person use. So you might ask, do we have any collaborative tools out there? Do we have tools that are designed for more than one person to use? Well, the simple answer here is yes, we do. We have tools that allow us to communicate verbally underwater. And here's the underwater cell phone and the GSM VHF unit. So you can see that both of these are full headgears. And the cell phone unit actually have a physical cord that connects the headset to the surface. And the other one uses the standard global system for mobile communication with radio waves in the range of 300 megahertz to 30 megahertz to 300 megahertz. Now, the obvious advantage of this is you can talk while you're underwater, but you can only do this if the person is using the exact same gear. Now, if you're trying to equalize pressure in your ears by pinching your nose when you're wearing all these gears, you might find it a little bit challenging to do. So with the underwater cell phone, there are actually a few other additional disadvantages. With the physical cord, if you want to swim around and try to explore caves and racks, there will be a few issues. You might get tangled up while you're exploring. And this particular model actually only allows communication between two people. So what do we need? Well, we need something wireless that can be used by more than two divers. And we probably don't want something that's a full face mask. So we found this. We found this dive computer that attacks the issue that I've described. Now, they were advertised to have the capability of sending preset messages to other people who are within the range of 500 meters. And when the message is sent, the receiving unit will get an alert. Another capability that they advertise is having the homing capability to allow divers to locate their boat if the additional boat unit is purchased. Now, there were limited information on the internet about this particular device, so we don't really know if it's only a prototype or if it's an actual device. But if it's an actual device, this probably still doesn't scale up. So now you know what the state of the art out there is. We want to look at a few questions that we still want to answer. So the first obvious question is, why should we do this? And then we'll go into look at what kinds of related work are out there for underwater communication, followed by exploring questions like, how well can communication scale? And how well can applications scale? And then we'll look at platforms that we believe to allow us to scale in the near future. So let's just jump into what we should do, or why should we do this. Now, as a tiny, tiny background, I'll tell you the rough estimate for the size of stakeholders that we're trying to serve here. So with just the PADI program, there are roughly 130,000 members. And the PADI program is only one of the many scuba diving certification program out there. So from these photos, you can see that recreational scuba diving, it's a highly social activity that involves extra equipment like regulators to help us breathe. But what if you actually want to communicate underwater? Well, if you try it verbally, you'll probably just get a stream of bubbles and a mouthful of water. So we usually rely on hand signals. But these hand signals could have a very different meaning in your day-to-day life. So now, I would actually like to ask, I want to see how many non-scuba diver, just by the show of hands, are in the audience. Awesome. This is super. Okay, so can I please ask all the non-scuba diver to just have a wild guess what this hand signal actually means? Okay. I'm here. Sorry? Taxi? Cool. Any more?
Problem. Like you need ship and assistance.
Sir.
Like there's a problem. Maybe your gear's coming apart.
Okay, yeah. All right. Any more? Okay, they're all very, very good answers. Now, the actual meaning of this, it means help. So to me, my first instinct, I thought that person was just waving at me. So I'll be very polite. I'll just stand up here, and I'll smile, and I'll wave back and say, hi, hello, when they're actually trying to get me to help them. So, okay, let's look at a second one. What do you think this one means? I can't hear? You're crazy. I'm feeling dizzy. That's very, very close. Any more?
Some sort of pressure problem that's happening?
Okay. All right. Those are all very good answers. So the actual answer is I'm feeling nauseous. But we can see that there's so many other meanings out there for this. Okay, so let's look at a third one. This is the last one that I'll just sort of test you guys on. What do you think this means? Nowhere. Yep, go up. Okay, so somebody actually had it right. This actually means I'm out of air. Now, so from this little exercise here, we can see that there are multiple meanings to a single hand signal. And even though all the hand signals are universal to all the scuba divers, and everybody is supposed to know about them, it's not really the most intuitive thing that's out there, and it can easily create miscommunication. Now, because of all the possible miscommunication, we need a tool that we can support collaboration and further enhance the communication between these divers. Now, not only do we want to support collaboration, we want to support scalable collaboration. And we want to look at how we can do that at both the application level and the system level. So what we've been talking about here relates to scalable ad hoc underwater network. But before we actually dive into the real literature, we'll just look at a few things for background purposes. So you might wonder what kind of things this kind of network could actually apply to. Well, there are a few, these type of applications can be related to, say, transportations or military activities. Some examples would be a marine accident investigation, military demands like submarine tracking, and underwater research in general. And if we look at underwater sensor network in particular, applications can involve underwater data collection, pollution monitoring, and autonomous underwater vehicle. Now, other than knowing the various areas that we can apply to, we also want to look at challenges in this type of network. Now, it is natural to have latency in our environment because this is caused by water conductivity. And from this equation, you can see that this is dependent on things like temperature, salinity, and pressure while it's underwater. So regardless of the type of technology we use, there will always be issues with latency and bandwidth. So to get a better idea of what kind of challenges we face in this type of network, we'll look at two common problems that we've seen in papers that we've came across. So the first one we'll look at is GPS. Now, because we wish to allow individual nodes to know their current position, our first thought would be, why don't we just use GPS underwater? Well, GPS actually gets quickly absorbed by water, and they can't really propagate that far deeply under the water surface. So we can't really use that. Now, the next one that we're going to look at, it's acoustic. So with acoustic, we have challenges in things such as communication range, channels, and bandwidth. So for communication range, it operates at a very low frequency wave, and so it has a longer communication range than radio underwater. Now, with channel, there are only a few channels that are available to acoustic networks. And communication speed is actually very, very slow. And with bandwidth, same thing. It has a very low bandwidth. So there are the challenges, but how do these units actually communicate? What are the possible routing methods? So today we're going to look at two. We will look at proactive and reactive. Now, Proactive routing is using GPS. Usually used in GPS system, where all the nodes are consistently exchanging routing messages, trying to maintain a sufficient and fresh network topological information. And with reactive routing, it is actually triggered by communication demand at source. So what it does is it will first flood the network, and it will wait for a reply to try and see what their path is, or how they can get to their destination. So the next thing that we're going to look at is what are the actual existing solutions that are out there right now for a problem. Well, one solution is to deploy multiple underwater sensor nodes that interconnects with underwater sinks through acoustic network. And these underwater sinks will then relay information to the surface. An alternative is to have an architecture that uses a large number of nodes to locally monitor and try to report any non-accessible underwater events through the use of community-based forwarding. So similar to all the environments that we've been talking about so far, the Nemo 2020 also operates at a highly dynamic mobile setting. And we also want to support communication for not only small groups, but also large groups. So in our proposed approach, we're using a hybrid network scheme, and we want to use multiple technology to create a seamless network for the scuba divers. Now, for all the underwater communication, we're proposing to use acoustics. And for any surface communication, we propose to first rely on radios, and then if the receiving surface unit is a little too far, we're gonna use alternate methods. So like a lot of our related work that we've presented today, due to the bandwidth and bandwidth constraint, our approach will also use the reactive routing method. But even though we propose something like this, if we don't have enough funding to test this in a real setting, what can we do? Well, one of our ideas is to try and emulate this network with one laptop per child. So by default, one laptop per child uses the 802.11s technology, which focuses on mesh networking. Now, it looks at how wireless devices can be interconnected to create an ad hoc network. And each of these OLPCs can act as a router, a data sink, and the data source itself. So we can also use an 802.11b or G router to act as the surface unit. Now, during our tests, we can also simulate changes by physically moving these OLPCs. And so here we have a big OLPC swimming farther away from the small one on the right side of the screen. And we can see that the direct connection just disappeared. But that far right OLPC will still be able to communicate with the big one based on the fact that they have nearby nodes, and those can relay the messages. So even after we have designed the communication scheme for the big picture, we also really want to look at scaling at an application level. So in our paper, we've talked about a standalone mode and collaborative mode. Because we're looking at scalability here, we want to focus only at the collaborative mode and how application can support scaling. So the first thing that we're going to look at here is the relative positioning screen. And this screen allows divers to not only view positions of anybody, of other divers in their own group, it will also allow divers to look at positions of people who are using the Nemo system but are not part of the same group. So here we can see that the dot in the center represents the dive computer users themselves. Any triangle represents any other divers who are in the same group. And the square represents any other divers that are outside that group. And to accommodate scalability, we're allowing divers to zoom in and out, much like how Google Map works. So here as an example, this can zoom to a bigger view, and it can zoom out to an even bigger view. So with our bar graphs, we are showing the status of, here we have a bar graph that shows group status, but you can see that it will quickly get cluttered. And that's why we're also providing a table screen, or a table view. So with the table view, you can see an abstract view of all the members that are in your group. And here, since we're encouraging localization, we will only let you to read data of members who are in your own group. Now, there are also liability issues here if we want to implement this feature. This is due to the fact that the dive master will be able to monitor all the air of other people. And if there are accidents or death that is related to air being low, now the dive master will be responsible for it. So as important as designing the right application and the right system, it is also very important to choose the right platform to build up on. So we had a chance to glimpse at 3 different candidates. We looked at TinyOS, the Android, and the iPhone SDK. So here in the first figure, up top here, we can see that all the underwater nodes are interconnected, and the communication between the underwater nodes and the surface nodes go through a gateway node, and that gateway node will convert radio waves to acoustic wave and vice versa. And the protocol stack is actually shown here in the second picture. And the details you can actually read in Yoon's paper, which we cited down here. And the important thing to note is the gateway node was actually recently developed on TinyOS. So this shows that it is actually possible to take TinyOS underwater. Now, in order to test and see if Android is possible to be a platform to build up on, we've tried to run a few graphic-intensive Android applications, and one of them being Global Time. So what Global Time is, it's a 3D world clock that was implemented in OpenGL. You can spin the globe around trying to look at different areas. And you can also look at the time that is corresponding to the area that you're looking at. Now, other than graphic-intensive applications, we've also looked at the top 50 application in the Android Developer Challenge. And what we're trying to do is trying to draw connections between our design and the current concept out there to see if there is a potential to try and transition Android and take it underwater. Now, we looked at the free family safe application where members can cross-check each other's statuses. And we also looked at the Ready Emergency Manager, where devices will stay connected even if the infrastructure fails. We also looked at Social Monster, which is an application that allows anybody in the ad hoc network to try to send messages without using accounts. And based on these applications that we've seen, we can see a potential in attempting to use Android as the platform to develop on for our project. And some of the things that we foresee Android to support for Nemo 2020 are things like 3D mapping, trying to help us do navigation and positioning, and image matching for photos that are taken underwater and can instantly identify the different species. But there are actually a few drawbacks with using with Android-specific implementation. And by that, we're referring to the lines of code that are required, that requires the Android API. So we've looked at a few open source stuff, both from the official Android site as well as third-party sites. And it shows that a large part of the code have a direct relation with the Android API. So if we look at the Notepad 3 code here, it turns out that excluding all these comments, 86% of these code are Android related. And for this reason, it leads us to wonder if there are actually other platforms out there that we can look into. So we've actually bumped into the iPhone SDK. We were watching, while we were watching the Worldwide Developer Conference keynote. And so it will be another candidate that we will invest more time into along with Android. So the key question here really is, do we want to use Android? Or do we want to use iPhone as our platform to develop on? Now, even though what we've been talking about today relates to the underwater world, we really can abstract these to other ad hoc network settings. And we can actually move this into applications for search and rescue teams. So an example would be relief team going into a disaster area after things like earthquake, typhoon, and even hurricanes like the Katrina. And that's the end.